linear model into a non-linear one. Okay, so as I told you, there are different types of hinges which is available in ETAB. Now I am coming to the ETAB software things. So once you say ETAB has got different types of hinges. One is called as a coupled hinges and one is called as uncoupled hinges. Now what is the difference between these two? These are the independent hinges. Independent hinges means what? Now let me explain this. Now let's say you have got a column here and the force applied on the column is equal to P. And then on the cross section level, you have got two different moments. One is M2, one is M2 at this level, M2, and another one is M3 on the other side. Let's say on this particular and this particular side, on this particular side, this is M2, M3. Okay. Now, when these two types of the moments are there on the column, along with the axial load, they are all interacting with each other. They are all interacting means okay, let's give me an example. I will give you an example. Let's say my force on the column, axial force on the column is 100 kilonewton. And at the time of this 100 kilonewton, the moment in one direction, let's say it is 150 kilonewton, and another direction, let's say it is 200 kilonewton. So this is one load case where the axial force P equal to 100, M2 equal to let's say 150, and M3 will be equal to 200 kilonewton meter. So these are the moment for the axial load of 100 kilonewton. Now, once I change this load and make it 50 kilonewton, this moment M2 and M3 will also change. This will also change along with this, right? So all these are dependent to each other. One parameter, if you change, the other will change. Or if you remove one parameter, make it zero, that will affect the other two parameters. Okay, so these are all three quantities which are interacting with each other. So they are called as coupled type behavior. So they are coupled with each other. That's why you have got an interaction diagram PM to M3 when you design your column. And to establish the interaction type behavior, you need the interactive hinges, right? It should not be uncoupled hinge, right? So you can see here there is interacting PM to M3 hinge that you can use for your column, right? Now let's take an example of beam. Beam is a member where your main behavior is a flexure one, right? So deformation, flexural deformation is predominant in case of beam. There you can use this M3 hinge only, where it is not interacting with other things. Okay, and of course, when you use this M3 beam, M3 hinge, you also need to use this shear hinge for the beam also. That is your another hinge, because this will simulate the shear behavior. This will simulate the flexural behavior for the beam, and for the column, PM2 M3 behavior will be simulated using this hinge, right? And then of course in the hinges itself you have got the selection that whether you want to use the plastic hinges or maybe the fiber hinges. So you can also assign a fiber hinge to the column, which is PM2 M3 fiber hinge, or you can use this interacting PM2 M3 hinge as a plastic hinge to the column, right? Now the question is why where we need to assign these particular hinges. They are generally assigned to the joint, and the question is why? Because the joint is the thing where it is stress more. So if you apply a lateral load on the member, these particular joint are stress more. That's why we follow the ductile detailing. So the most of the nonlinear behavior is concentrated at this level. Most of the nonlinear behavior is concentrated at this level. That's why we assign the hinges at the end of the beam, not over the in between. So in between we can safely assume, again this is an assumption, safely we can assume that this particular element will remain elastic. and at the end the plasticity is lumped, right, with the help of all these hinges. So this is these are the types of hinges which is available in software to incorporate all these types of the behavior. You can assign a single hinge, you can assign a number of hinges to the particular object, maybe in the form of shear or in the form of moment, or interacting type hinges, shear moment interacting type hinges, or maybe force moment interaction type hinges, right? Okay, now the question is whether we need to assign the hinges to all elements. Well, it depends upon your judgment, right? So let's say if you have got a structure with say 1000 number of columns, and then there may be 3000 4000 numbers of beams, and you need to perform performance based design or nonlinear analysis for that particular structure. So it is not feasible at all, such a huge structure, it is not feasible to assign hinges to all the elements. Okay, you can distribute the inelasticity on the structure level also. Let's say this is your structure with certain geometry, and you know that the structure is stressed most at the peripheral level, right? So you can distribute, you can select the members at the periphery of the building, which will behave in a non-linear fashion or in a inelastic way, and other members you can consider as a elastic one. That is also possible. Okay, so it is not compulsory that all elements at all levels you should lump your inelasticity. Your model in that case will become complex, and the solution generally will not means it's a iterative process and will take considerable time, right? Okay, so that approach is also possible for nonlinear modeling. Okay, now let us see this in software, one by one types of the hinges. I will also show you in the hinges available in the ETAB, and then how you can interpret the data for that particular hinge. This is the first hinge, which is called as a beam plastic hinge definition. Okay, so let us first concentrate on beam hinges. So as I told you, let us first see what type of interpretation is required for assigning this M3 type hinge. So it is a M3 type hinge. First, I will tell you where to go to in this particular form. Okay, so let's go back to the ETAB now, and then we will continue this discussion. Okay, so let me open the ETAB. Okay, tell me whether it is visible to you or I need to share the screen. Just hold on, I will share. Let me share the screen itself. So is it visible now? Hello?
Yes, sir.
Okay, fine. So the first point for converting your model into the nonlinear model is that you need to define the material nonlinearity. The material nonlinearity. Where to define the material nonlinearity, that I will show you first, and then I will go to the plastic hinge assignment. Okay, so here you have got the material definition. So let's take this first part, that is define material properties, and then I am going to define M30 material as a trial one. So say add new material. Here M30 properties is there. Now once this form is open, there is one thing that you can do is a nonlinear material data. You can observe this here. There is a tab called nonlinear material data, right? So all these properties you know how to assign, or it is by default the ETAB can take directly the weight of the material or modulus of elasticity, constant modulus of elasticity. But this nonlinear material data is a new form one. So this is the first parametric input you need to give to ETAB. So let's open this. So once you open this, you will see this particular form, okay, where there are certain performance levels which is already defined, that is IO, LS, and CP. that is immediate occupancy, life safety, and collapse prevention. So these levels are already defined here with certain values inside this particular boxes. Okay, so what are those values? Let us check on the curve first. So you can actually check this stress strain curve, show stress strain plot. So you can open this plot, and then this is your stress strain behavior for M30 type concrete. Now here, these points, these colors will represent these different levels. So you can see here IO level is somewhere here, and then LS level is there, and CP is not there. Okay, so CP is outside the graph actually. So first thing you need to do is to modify these figures. You need to modify these figures. Otherwise, your design non-linear material properties may not be correct, right? So how to modify it? You can see that you can set your IO level maybe somewhere here. That is better actually, right? So where the material just started yielding, at that point you can set your IO level, and the strain at this level is roughly, you can say it is 1 point or maybe 1.6, right? So 1.6 into 10 to the power minus 3. So it is 0.0016, right? So you can set your IO level at 0.0016. Let us change that value here. So IO level I am going to save instead of 0.003, I will make it 0.0016. Okay, and let's check the graph now. Now see here, this point is now shifted. Okay, so it is at this particular location. Okay, in the curve. Now IO level is set. Now let us set this LS level somewhere here, where the material is actually started yielding and losing the strength of the material. Is started at this point. Let's say it is at this level. So it is at 3. So let's set this LS is equal to 3. So it is 0.003. So I'm just changing these parameters for using it to nonlinear analysis. So it is now set here. And at the last point here, let's say here, the collapse prevention level will be there. So let's say it is at 5 or maybe 5.6. Okay, so let's take it as 5. Okay, so 0.005 will be my collapse prevention level. So 0.005. So minus 0.005. Okay, so let's check. Now all these three levels are set. So when my material will start yielding at this particular point, which is IO level, and then it is at LS level, and then my collapse prevention will be somewhere here, where after this point there is actually degradation of huge degradation of the stiffness, and then material collapse will be there, or the material will actually lose 100% of its strength, right? So this is on compression side. This curve representation of this curve is on compression side. What about tension side? You know that concrete has got very less strength on the tension side. You can neglect this strength also, but it has set by default with some small value, and then it is immediately degrade, and it becomes zero. Strain will become zero after this point. So let it be default. So this is how you can set your stress strain material curve for the concrete to be used in the nonlinear analysis. So this is the first step. Okay, so now these levels are set actually. Now the next thing is you need to give the hysteresis data to the concrete. So here you can see that this hysteresis type is considered as concrete, right? And then you can check this hysteresis. There are some default hysteresis data you can use. One is elastic, kinematics, then Takeda model is there, pivot is there, and then you can go to this reference manual and check these different curves which is available. The most suitable one is concrete, right? Hysteresis type, you select it as a concrete and check this hysteresis parameters. Once it is open, he will ask you the energy degradation factor. Once it is open, the program will ask you how much energy degradation factor should be there. Okay, so that you have to decide based on the degradation of your loops. So let's say, suppose this is actually a ratio between the area of the loop in a undegraded position and area of the loop in the degraded position. So degraded divided by ungraded. So it will be actually in the form of point, okay, less than 1. Okay, so if you, let's say if you keep zero point 0.5, this indicates that the area of the loop in the degraded portion is 50% of the area of the loop in undegraded portion, right? So that you can set, that factor you can set here. Okay. And then stress strain curve definition, there is a already inbuilt definition available. One is the Mender model and one is the simple model. Okay, so you can check this Mender model also. Here, if you open, you will find this different A, B, C, D point on the curve, right? So this is by default is used by the program. You can change this stress and strain value if you want for any of the parameter. So that is possible. So this is parametric, so that you can use. Then there is a strain at unconfined compressive stress, so compressive strength of the concrete, right? So this is a strain. Okay. Now here you need to remember one thing. This is very important as far as these material properties are concerned, right? So what is this FCK? FCK, what we are using is not the value of actual characteristic strength of the concrete for nonlinear analysis. I'm just talking about the nonlinear analysis. It is expected yield strength or expected characteristic strength of the concrete. That means what? That means for M30 concrete, you cannot use M30, that is 30 Newton per mm square, for nonlinear analysis directly, even if by default the material gives you 30 Newton per mm square, right? So it is always an expected strength. It is always an expected strength, and that you need to change while defining your material. And generally, the expected yield strength is 30% more than your actual yield strength of the material or the characteristic strength of the material. So let's say if you are using, say, M30 concrete, so you just straight away multiplied it by 1.3, calculate that value, and that you put as a the strength of the material or the characteristic strength of the material. It is always expected strength that is used. Okay, so here the strength you can see here, whatever the stress this material is using now, it is around 30. Okay, so we have given it 30, so it is using 30. So we don't want this program to use this 30. So it should be around 1.3 into 30. Okay, so that you change at the material level itself. So this is your preliminary data, nonlinear material data that you need to assign to a program. And then you can check this plot also after assigning all these parameters. And then one more thing you need to do, as I told you, you have to change this particular stress level for M30 material. So now here, as I told you, this is very important thing that you need to modify. So design property data, if you click on this, you will get a form here, and here the strength of the concrete is used as 30, that you can modify it to 1.3 into 30, whatever the thing is. So it is around 39. So you use this 39 value as a cube strength of the concrete for material data. Okay, so this is the first thing you need to do for performing the nonlinear analysis, right? So that is over now. The other properties are there, but that we will keep it as default one. The most important thing is nonlinear material data that we have already set. That means IO level, LS level, and CP level. So that's it. So this is the first thing. So my material definition is over. Okay, now we can proceed further for defining the parameters. The next parameter you need to define is the plastic hinges. Right, so how to define the plastic hinge? For that we need to go to define section properties, and here the frame wall nonlinear hinges are available, right? So if you say add new property, and let's say it is concrete now, and say okay, So here you will find this all these different hinges. Okay, so let's say I want to assign fiber hinge to the column and plastic hinge to the beam. Fiber hinge to the column and plastic hinge to the beam, right? So let's first take the fiber hinge, right? So fiber hinge is PM to M3 hinge, right? So fiber PM to M3 I have selected, and then he will ask you whether the fiber property should be used from the default frame section or it is user defined. What does it mean? When you say, okay, use these fiber properties from default frame section, that means what? Whatever the properties you are assigned to your frame section definition, that is used for calculating the fibers automatically by program. You need not to interfere with that particular property. Now, when you select its default, you must ensure that after linear analysis, whatever design output is there, that is incorporated in frame section properties. That should be incorporated in frame section properties. Then only you can use this default frame section property. What does it mean? Let me show you that. Okay, so let's say there is a linear model. You have already done analysis and design of that particular model, and you have got the sectional properties along with the reinforcement. So that information you must give to the program one by one section. For every section you define here, let me show you. When you add your section after designing, right, after finalization of the design, so let's say I want to add a beam. So say add new property. Let's say it is concrete. So let it be this material. I will choose, let's say, M30 concrete, and say my beam is say B 300 by, or let's say column it is. So let's say column say 450 by 450. Okay. So I will just put this dimension 450 450. Okay, and then when you say modify show rebar, this new window will appear, and you must be wondering up till now why this data is there in the program itself. But we are not using this data when we define our sectional properties. Now for nonlinear analysis, this data is used. Okay, up till now we have probably not used this. Of course, you have to set this longitudinal bar and confining bar rebar type. And then you have to put all your longitudinal reinforcement, cover to the longitudinal reinforcement, number of bars in X and Y direction, whatever, with diameter and their area. Along with that, you also need to put as a input the confining reinforcement, which is your design data, which is your design output. Everything you have to incorporate in this particular section. Okay, and then when you say okay, and then let's say when you go for the section designer, sorry, section hinge assignment, frame section, add new property, concrete. Here, if you select, let's say PM to M3 interacting hinge, sorry, fiber hinge, right? And then when you say default, now that default sectional properties will be used by the program. And if the reinforcement data is not there, then of course you have to go for user defined things. And for user defined, you need to define the fibers. So this data will appear when you select user defined fiber hinge. So what does it mean that this is your section, whatever section you are using, you need to define each and every individual fiber for that particular column or by for that particular hinge. That means what, you can divide your cross section into number of parts. Maybe for this column, you can divide it into the 9 equal parts in a horizontal as well as vertical direction. So, and for each of this cross sectional area, you need to define one separate fiber for that. Okay, so let's say for example here there are these are the fiber properties. These are the fiber properties we are going to use. So let's say this small area is there where we want to define our fiber with a cross sectional area of that small portion of your cross section is, let's say it is 50 centimeters square. small area, right? And the coordinates of that fiber, that means I am talking about the centroid of the that particular fiber, can be entered here. Okay, so let's say it is at, let's say it is 100 mm from this point. Now you can see this point is shifted here. Now it is blinking somewhere here. So this fiber is here now. This fiber is here. You can put minus as a coordinate also, right? Or plus as a coordinate. And then there are two options, third coordinate and second coordinate, like that also. Okay. And then you can select your material from your material list. And then there are two types of the stress strain core which is available, which is SSC1 and SSC2. Okay, so this is how you can build your own fiber if you go by the manual fiber definition. This is for manual fiber definition. You can add the number of fiber, it is possible. So many fibers you can add for a single column, and then you can design, means you can define that coordinates material for that particular fiber, and then the program will use this as a input data. Of course, you should remember that these fibers, whatever fiber I am defining, this fiber should be separate for longitudinal reinforcement and separate for your concrete. This should not be combined. So maybe let's say if you have got 4 bars in this particular row, 4 number of longitudinal bar, for this all 4 bars, you can define a single fiber with at their centroid as a one fiber. So that is possible. Okay, but it should be separate because the properties are different. Here, there the material will be steel. Here the material is concrete, right? So the properties are different, right? So that is how you can go for the manual definition of the fiber, right? And then if you, let's say I use this fiber FH1, okay, which is already defined as a force fiber PM2 M3 hinge. So that is added to your defined frame section properties. And let's say, okay, now it is added. Now this fiber you can assign to your column by selecting the column. Let's say if you have got a column like this, any column, let's say I just keep this default properties, and here you have got the column, and then you can select this column and then go to assign and then frame section and hinges. Okay, here you will find that there are two properties. One is your defined properties, which is FH1. Just now we have defined, and say another option is auto. So you can go with this automatic hinge assignment option, and then he will ask you what type of hinges and what type of hinges you need to assign to this particular column using which standards. So there are certain inbuilt hinges, like say for example ASC 4117, that you can use, or maybe the hinge type table, it is for flexure, it is for column, or maybe for another types. So all are inbuilt. Here you need not to give any parameters, they are all inbuilt, right? So you just select this column, say it is default, and then say okay. So that is possible. Or you may go for the fiber type hinge just now you have defined. So let's say if I go with this FH1 type hinge, then he will ask you, program will ask you where this fiber to be assigned. At the ends means at 0 and then at 1, you need to add this. Let's say this is at 0, and then of course I will put 1 add. Okay, so this fiber is assigned to this particular member at 0 and at 1, and just say okay. Now here you can see this fiber hinge is assigned. Where it is assigned? At the ends of the columns. So this is a fiber hinge assignment for the column. Now similarly, there are number of hinges which is available in the ETAB, and the curve for that particular hinges, you need to understand that. Okay, so let's go back to our discussion, and we will quickly look at the curve, what is which is inbuilt as a hinge property into the ETAB. Okay, so let's go to the curve here. Okay, So this is one of the plastic hinge, which is a manual plastic hinge, which is there in your ETAB, and each term has got its meaning. Okay, so I have tried to define the all terms in a single slide so that you can understand. So here you can see that the first property is moment by scale factor. What is this scale factor? This is nothing but the yield moment. So it is a normalized moment. It is a normalized with yield moment. So moment is generally normalized with yield moment. And of course, the rotation is also normalized with yield rotation, normalized with yield rotation, right? Now you can see here, this is one of the graph for the particular hinge which is defined here. And then the one important thing you should note that this graph is straight from this point to this point, and then it actually start. What does it mean? Actually, the non-linear hinges will only activate after the yield point. So this is your yield point actually. The structure is yielded, then only the hinges is activated. Unless and until the structure is within elastic range, your yielding of the hinges will not reflect, or there is no data you can extract from the hinge properties after analysis. There is only data when your hinges yielded. That means what? Your load magnitude should be such that your hinges started yielding. Okay, and then there are number of points actually on this particular curve. This is A point, then B, C, D, and E. And then the program will ask you what to do to this particular hinge after E point. Whether it will exceed like this, continue like this, or come to zero. Okay, so that data also you can set here. Okay, so if you want that this point should drop, then say drop to zero, or otherwise it will extrapolate from this point and go as a straight line. Then the program will also ask you whether you want to use the moment rotation type behavior or moment curvature type behavior. Okay, so generally we select this moment rotation. Even if you select the moment curvature, it converts this moment curvature relationship into the moment rotation relationship, right? Okay, and then of course the moment curvature hinge length he is asking. Now what does it mean, hinge length? As I told you, it is a distributed elasticity model. The hinge can be concentrated at some location, or you may assign the hinge with certain particular length. That means the distributed elasticity is having certain length. Let me explain this. Let's say this is your member. Let's say this is your member, and then I have selected certain hinges, and then I can assign the hinge up to this length from bottom to top at both ends, and this is this input. Okay, sorry, this one. Okay, so how much length you want that your hinge should be there, and other part will be elastic. Okay, so that is your moment curvature hinge length, right? So hinge length to be given. Then he will also ask you, this is a plastic hinge definition for beam, right? So he will also ask you which type of model you will be using for simulating the hysteresis behavior, right? So there are different inbuilt model available. Hysteresis behavior, we have already discussed this type just now. Okay, so there are Takeda model available, then there is a degrading type model available, concrete type model available. For beam, these two models which is highlighted here, Takeda and degrading, that is mostly used. You can use the other type of models also, and then in that case you need to input certain additional data also, right? So all these models are available. Now here you need to put this factor as a 1, because as I told you, this graph is something like this. So it start with this particular point, and that's why this slope factor should be equal to yield moment, and that is equal to 1, right? So you have to put this as a 1, and once you put this, why this graph actually started from this point is again a question. Why not from this point, or why not your hinge will be like this? Let's say why not it is like this? Why not it is like this? Maybe whatever properties you are using. Same thing, but I have started this from the zero, right? So this and this is same, but this graph is started from this point. Now here you can see that it is starting from this point because the program actually knows the elastic behavior of the your member. He knows already that the elastic stiffness is this much. Okay, and then only he can incorporate the yield stiffness or yield properties to the structure, right? So elastic stiffness data is already known by the program, and that's why this inbuilt graph is not like this, it is not like this, it is like this. Okay, whatever shown here. Okay, so then there are different ordinates of this point. You can, of course, you can change all these parameters, they are editable. Even the levels of your performance objective also you can change. Okay, so this is a plastic hinge definition for beam. Okay, so I hope ki most of the things I have covered in this plastic hinge definition. Actually, these are a very detailed topic, and then you need to refer this ASC 4117 first, FEMA guideline, that is second one. Then your the modeling parameters, that is your reference manual for this ETABS for nonlinear parameters. Each of the term in this definition is actually consume lot of time to understand correctly, but I have tried to explain you most of the things in the hinge definitions. Okay, like that, there are many hinges, like M3 plastic hinge is also there, and then you can compare the manual and automatic type hinge. What will be the change in the parameters? What type of parameters to be incorporated in manual, and what are requirement for automatic hinge generation? Right, the most important thing that these are the inputs required while you define your hinge properties, right? So you know, you should know the yield moment, yield rotations, ABC point, IOLSCP, and then this is the reinforcement ratio, shear reinforcing, all these parameters, then hysteresis model that you are going to use. As I told you, there are different hysteresis models available, so all these information is required before going for plastic hinge modeling. Now let us quickly look at the column plastic hinges, because